Hello everyone, welcome to lecture 10 and module 5. This is the last theory lecture in this course where we are going to discuss about the Cayley sand analysis. So the last two modules have been about the interpretation of well logs in our Cayley sand. So in Cayley sand analysis, we have discussed about how to calculate the cell volume and the effective porosity of the formation. We have also discussed about what are the different effects of presence of cell in our well logs. For example, we know that the cell can provide excess conductivity due to which the formation water saturation can be overestimated. So today we are going to discuss about this cell access conductivity in detail and how the well log data in the presence of cell can be used to interpret in terms of effective water saturation and the total water saturation. So different series and water saturation model will be discussed in today's lecture. So the first step in the Cayley-Sand analysis, that is the cell volume calculation, and the effective porosity calculation, that is the second step, have been already discussed. Now the third step, that is the effective water saturation calculation, will be discussed from the residuity log data. So we know that the cell can provide excess conductivity due to which overall conductivity of the formation can increase, and if you use the RC equation we are going to overestimate the formation water saturation. So this part we have already discussed in the last lecture. So let us first understand how cell can provide excess conductivity, how the current can flow through our clay layers, and how we can exclude the excess cell or clay conductivity to calculate the true water saturation inside our pore spaces. Then you will be able to understand how different water saturation model works in our Cayley sand analysis. So first, for a clean formation where there is no cell content or we have very low amount of cells such that its effect is negligible, then there we can define our classical formation factor or the formation rigidity factor as Rho by Rw. If you use the conductivity instead of rigidity, because many of our Cayley sand analysis model, they are given in terms of conductivity, so we can define F also in terms of conductivity. So I will replace the rigidity terms in terms of conductivity, and then the equation of F will become as Cw by Co, where Co is our conductivity of the rock and Cw is the conductivity of our formation water. So Co can be written as Cw divided by F. That means conductivity of the rock is equal to the conductivity of the formation water divided by the formation resistivity factor. So a graph between Co and Cw will be a straight line going through origin with slope of 1 by F, like here. Now let us consider if I have a Cayley formation. So the conductivity of the formation is going to increase. So what is my conductivity of the formation? That is Co, and this is the conductivity in our clean formation due to the flow of current through the formation fluid inside the pore spaces when cell is present. So the clay layers or the clay inside our shell can provide excess conductivity. So this is the excess conductivity provided by the clay inside our reservoir rock. This is marked here in this figure as X. So this is my conductivity due to our formation water inside our pore spaces, and then excess conductivity provided by my presence of clay. So generally we have a linear profile after certain salinity or at high salinity. In low salinity environment, this excess conductivity is variable and it increases with respect to increasing the formation water salinity. After certain time, how much excess conductivity is there, that will be fixed and it will not change even if the formation water salinity is changing. So whether the cell conductivity or the clay conductivity offered by the clay material will be more prominent, or our conductivity provided by our formation fluid inside pore spaces will be more dominant. It will depend upon the relative values of Cw by F and the conductivity provided by the clay, that is CCl. So in order to know which value will be higher, which value will be lower, we must first understand how clay can conduct electricity. So, before we discuss how clay can conduct electricity, I just want to show you this figure as well, where this is our Cw by Co. So, what is my Cw by Co? Cw by Co is formation factor in case of a clean formation, or if we have a shelly formation, we can call it apparent formation rigidity factor. We can see the presence of shell decreases the value of our F. But at high formation water salinity, both shelly sand and clean sand will have almost same value of formation factor. That means at high formation water salinity, the conductivity offered by our formation fluid inside pore spaces will be so high that the excess conductivity provided by cell will be not significant. In that case, our Archer equation may be used to calculate the formation water saturation. Now, let us first revise the concept of our shell. We know that shell is made of clay, it carries negative charges. So, we have already discussed about the cell chemistry, where we have discussed that cell is made of different seed, that is the tetrahedral seed and octahedral seed, and in order to balance the negative charges, we have cation inside our this seed structure, but sometimes higher valence cation can be replaced by the lower valence cation inside our clay structure. That's why clay carries negative charges. So these negative charges of clay are balanced by absorption of water and cation or the layer surfaces. So cations are absorbed to balance out on the negative charges along with the water molecules. Now these cations which are absorbed on the our clay surfaces, they are called exchangeable cations because these cation can also be replaced by some other cations. They are not permanently bonded on the clay surfaces. So any cations such as sodium, potassium, if they are absorbed on the clay surfaces which are balancing out the negative charges of clay, can be replaced with any other cation. That's why they are called the exchangeable cations. This is the main reason for the our excess conductivity offered by the shell. These exchangeable cations which are present at the clay surface can provide additional path for the current to flow, thus clay material can conduct electricity. Now different types of clay will have different cation exchange capacity. So what I mean by the cation exchange capacity? So cation exchange capacity, it defines the amount of exchangeable cation in the clay. That means how much amount of cation is present on the clay surfaces. So if our clay surfaces have more negative charges, they will have more exchangeable cation on the clay surfaces to balance out our negative charges. So we can say that the larger the cation exchange capacity, the more will be cation the clay can absorb. And these exchangeable cations, when they are printed inside an electrical field, they can flow because they are not permanently bonded on the clay surfaces. And in the presence of an electrical field, these cations will flow and provide conductivity for the flow of the current. So this way the clay will have certain conductivity. And the amount of exchangeable cation is defined by the cation exchange capacity. So cation exchange capacity is generally measured in terms of milliequivalent per 100 gram of clay or centimole of positive charge per kilogram of clay. So this is our cation exchange capacity, and this units represent that how many numbers of exchangeable cations are present inside our formation at the clay surfaces. So if I want to know that how much conductivity is offered by my clay, so I can measure the cation exchange capacity. If I get higher cation exchange capacity, then I can say that my clay have more number of exchangeable cations. So if printed inside an electrical field, it will provide more conductivity for the flow of current. So cation exchange capacity CEC or QCEC can be a direct indicator of our conductivity of the clay inside our reservoir rock. Now let us discuss this further. So the conductivity of the clay can be defined by the or explained by the help of electrical double layer concept. For example, if I have a negative surface just like clay, there will be a positive ions near the clay surfaces which can be strongly absorbed on the clay surfaces. And as we move away from the clay surface or the negatively charged surface, I will have more positive ions because negative charged surface will attract the positive ions. So positive ions will be concentrated near the this negatively charged surface. But as we move away from the surface, the positive ions will diffuse and the concentration of the positive ions will decrease and the concentration of negative ion will increase. Just like in this figure you can see, if I have negatively charged clay surface, we can see the positive ion concentration is higher near the surface because negative ions or negatively charged surface is going to attract the positive ions, and then as we move away from the clay surface or the negatively charged surface, the negative ion concentration will increase, and in the bulk solution further from the surface we will have almost same amount of ions. So this way we can see that near the clay surface we have excess concentration of our cations or the positive ions. So if I visualize this in our reservoir formation, so this is our sand grain, this is our sand grain, and we have a dispersed clay here. You can see this is my clay material and the clay surface have negatively charged ions, and the positive ions are near the clay surface. So positive ions or cations are concentrated near the our clay surfaces. Now to visualize it further, you can see this is my clay crystal, and you can see there is strongly absorbed water layer near the clay surfaces to balance out the our negatively charged clay surfaces, and cations such as sodium ions are also present near the clay surfaces and they are in hydrated form. That's why they are not permanently bonded on the clay surfaces. In fact, these absorbed layer, the first layer of the water molecules, it has so much higher electrostatic force in between the clay crystal and the water molecule such that they are not movable at all. This is the region of existence of bond water, because the bond water is not mobile because the electrostatic forces are so high that you will need a very large amount of delta P or drawdown pressure to remove this water molecule from the clay surface. That's why these water molecules are not mobile at all. So this way we can see our excess cation can concentrate near the our clay surfaces, and when an electrical field is presented, these cations can flow in the presence of our electrical field. That's why clay can conduct electricity by providing additional path for the flow of the current, because the clay surface area is much higher than the our other types of reservoir materials such as our rock materials such as sand. So this excess concentration near the clay surface can be significant. That's why the excess conductivity of the Selly formation can be significant. That's why in Selly sand analysis we should consider both what is my conductance inside the bulk solution and what is my conductance inside the clay surfaces. So both the conductivity, that is the conductivity of the formation fluid in the pore spaces, and the conductivity of the excess cations present inside the clay surface must be considered to accurately estimate our true formation water saturation. We can visualize the current flow path in this figure. For example, in a clean formation, these whites are our grains and these colored are our flow path or the pore spaces present inside our reservoir rock. So we can see that this is the tortuous path followed by the current inside our reservoir rock. The current can flow like in this way by following this tortuous path. In case of our shelly rock, you can see these yellow ones are the clay coat, that is the dispersed clay model, where we have the clay printing in a way that they are coating our sand grains. So these are my pore paths. The blue colors are my pore path or the pore spaces inside our reservoir rock. Now if we compare with the earlier figure, here we had a pore throat. The current could still flow inside from this pore to this pore by following this path through our pore fluid. In this case, what we have, you can see the pore is blocked. The clay have blocked the pores. Now current can still flow inside my fluid inside the actual pore spaces by following a tortuous path like this. But if this clay is non-conductive, this current cannot flow here through the pore fluid. But now, since the clay is also conductive, we can see we have additional path for the flow current. So the current is also flowing through the a path which is concentrated near the our clay surfaces. So here against the pore throat, the current can also flow through this clay. You can see these are the additional path for the flow of current. So both the path, that is the path of the current inside our clay and the path of the current flow inside our pore fluid are available for the current to flow. Now, we have established that the cation exchange capacity, which defines the how much excess cations will be available near our clay surfaces, are responsible for the flow of the current through the clay structure. So we have already defined the cation exchange capacity. Generally, cation exchange capacity is also defined in terms of QV, where QV is defined as the volume concentration of the clay exchangeable cation, and it is measured in the milliequivalent per milliliter. So QV can be defined as QCEC divided by Vp, where Vp is the pore volume in centimeter cube per gram of our rock material. Because the cations can only conduct electricity in the presence of water when they are hydrated with water molecules. That's why QV is a better measurement to define our cation exchange capacity. That's why we have defined the cation exchange capacity by defining it as the volume concentration of the clay exchangeable cation in per unit pore volume of the pore fluid. So QV is defined as QCEC divided by Vp, or Vp will be can be written as 1 minus phi divided by phi into rho Ma, and the total conductivity of the clay exchangeable cations can be defined as CCl is equal to B into QV, where B is a parameter which is related to the our formation water conductivity, or the how much salinity of the formation water is there, and it can be calculated at 25 degrees centigrade as B is equal to 0.046 multiplied by in bracket 1 minus 0.6 E into raised to the power minus C by W divided by 0.013. For example, if you have dry shell or dry clay, it will not offer any conductivity. Only if the clay is present in the presence of a saline water, then only changeable cation or the cation can accumulate near the clay surfaces. If there are no cations are present inside the solution, you will not have any excess conductivity. So dry shell cannot conduct any current. So QV is also an indication of the degree of salinity of the formation. For example, QV less than 0.1 can be considered as clean sand. If QV is between 0.1 to 0.2, it is silly sand, slightly silly sand. 0.2 to 0.3, it is moderate silly sand. 0.3 to 0.5, it is should be considered as silly sand, and a value of greater than 0.5 should be considered as very silly sand. And the excess conductivity of the clay is dependent upon the CC of or the cation exchange capacity of the clay, and different clay will have different cation exchange capacity. As we have discussed, the clay structure of different type of clay are different. Some might have higher negative charges, some might have lower negative charges. That's why the amount of exchangeable cation present in the near the clay surface can be different. So you can see the kaolinite, it have the CC around 3 to 50 milliequivalent per 100 gram, whereas the illite or chlorite have only 10 to 40 milliequivalent per 100 gram, and montmorillite have 80 to 150 milliequivalent per 100 gram. So now, how to calculate the excess conductance or the conductivity offered by our clay? So in our rock conductivity model, when the clay is present, whether we have laminated shell or dispersed shell, we assume that these two conductive paths offered by our sand grains or the fluid present inside the pores between sand grains and the excess conductivity offered by the shell due to the negative charge of clay surface are working in parallel paths. That means we have a parallel connection between our current flow path offered by the sand and the offered by our shell. So conductance can be written as overall conductance of the rock, CO, should be written as the water conductance or the conductance offered by the pore fluid inside our pore spaces plus the conductance offered by the our clay material inside our reservoir rock. So this model can be used to our prepare saline sand water saturation model. Before we discuss different types of saline reservoir water saturation model, let us first discuss when we should use a saline reservoir saturation model. So we have discussed the effect of cell and how different log data are affected by shell, how rigidity or porosity data are affected by the pressure of shell, and how clay can conduct electricity. And so we can summarize, if VSH is high as seen from the log or core data, then obviously we should use a saline sand water saturation model. If CEC or QV measurement on core also indicate high values, that means we have enough exchangeable cations inside our reservoir rocks on near the clay surface, that means clay will have excess conductivity, so I should use a saline sand water saturation model. In freshwater formation, where cell effect could be more pronounced, there the conductivity offered by our pore fluid might be very low because we have less formation water salinity, then the conductivity offered by the cell could be significant or the clay could be significant. Then we should use a saline sand water saturation model. In high salinity, the effect of cell become negligible even with high clay content. As we have discussed earlier, the formation factor or the apparent formation factor in the presence of high water salinity will approach to the formation factor of a clean reservoir. Then we might use the RC equation to calculate the formation water saturation. So often what we can do is that if we are in doubt, the cell content value or the cell volume content is such that we are not sure which saline sand model to use, or we should use a clean water interpretation model or the RC equation. What we can do is that we can calculate the value of SW by two equations, one by our classical RC equation for clean reservoir and one water saturation from any of our saline sand water saturation model. For example, we can use a cell volume based model such as Indonesian equation and compare these two values. If these two values are closer to each other, that means we have less cell content or the effect of cell on the rigidity log is very less. So classical RC equation can be used in that case to calculate the formation water saturation. But if the values calculated by our Indonesian equation or any other water saturation equation differ widely from our classical RC equation, then it indicates that we have sufficient cell content and we should use a saline sand equation to calculate the formation water saturation, which can include both the conductivity offered by the pore fluid and the conductivity offered by our clay in our reservoir rock. So if you recall, we have discussed this in earlier classes. I have given you a very brief introduction. So if I have high formation water salinity and if I have low clay mineral content, I can use the Archie's equation. Even if I have high clay mineral content, I can use non-Archie's equation and I can use two types of model, that is the effective porosity model and total porosity model, to calculate my water saturation inside our reservoir. If I have low formation water salinity, then the effect of cell could be significant even if the cell is present in low amount. Then I should use a non-Archie's equation or saline sand water saturation model to calculate the effective water saturation. So these are different types of models that could be used. For example, effective porosity model could be Archie's equation for clean reservoir, then Indonesian equation, Samendo equation. Total porosity models such as dual water model and Waxman-Smith's model can be used to calculate the formation water saturation. These two models can be divided in terms of a VSH based model and double layer model. So a VSH based model, there we use the cell content values or the salinity of the formation to calculate the formation water saturation. That means input will be our effective porosity and the cell content or the salinity of the formation to calculate the formation water saturation. In double layer model, which are based on our actual physics of the rock, where we consider both the conductive path offered by the pore fluid inside our pore spaces and the conductive path offered by the excess conductivity inside our clay. So there the cation exchange capacity is included in our model. So Waxman-Smith or dual water model, they include the cation exchange capacity to actually incorporate the excess conductivity of our clay or shell, and and then they can provide the value of formation water saturation. So all these models, they try to model the clay behavior and prepare a water saturation model for saline sand by including the clay conductivity along with the formation pore fluid conductivity. So let us discuss some of the different saline sand equations. So first we'll consider a few of the cell volume based or cell content based methods. So these methods or these water saturation model, they take input of cell volume which may be derived from our gamma ray log or our density neutron cross plot or any other methods, and by using this cell volume they try to calculate the what is the excess conductivity offered by clay inside our rock, and then we can account for the clay conductivity, and accordingly actual or effective water saturation can be calculated from the well log data. For example, Samandu and the Indonesian equation, these are the one of the two most popular equations that are used for calculating water saturation in our shelly sand reservoirs. Generally, the Indonesian equation is used in non-linear region here or in the region of low formation water salinity, and Samandu equation is used in high salinity environment or in the linear region where the response of the shelly sand is linear to calculate the formation water saturation. So the first model, that is the Samandu model, it modeled the residue of water saturated shelly sand reservoir in this way. For example, in case of water bearing rock, general response can be written in form of 1 by Rho equal to alpha plus beta by Rw, and if we have a hydrocarbon reservoir, then 1 by Rt can be written as alpha Sw plus beta Sw square divided by Rw. According to this model, the value of alpha is close to VSH divided by RSH and beta is 1 by F. So this model the clay behavior by calculating the parameter alpha and beta this way. So basically this model have been generated based on the a number of data obtained from different core experiment. So rigidity of the core have been measured at different shallowness of the core samples, and this empirical equation has been generated. You can see the conductivity inside our reservoir rock will depend upon what is the pore geometry, what is the clay distribution, and what is the cell content, and what is the residue or the actual conductance of our clay material inside our reservoir rock. So you can see both alpha and beta parameter, they include the tortuosity, the cell content, and as well as the conductivity or the residue of our shelly formation. So 1 by Rt can be written as VSH divided by RSH into SW plus SW square divided by F into RW. And solving for SW, water saturation can be calculated according to this equation. So you can see in the final equation for water saturation, we have the input parameter VSH is required, or the cell volume, cell content is required, the cell resistivity RSH is required. That means we must have a pure shelly formation where we can measure the conductivity or the residue of the pure shelly zone, that is required. The formation water residue is also required. RT will come from the log data. Phi, that is the effective porosity, must be measured from any of the logging tools. And value of C for sandstone can be taken as 0.4 and for cormet can be taken as 0.45, and SW can be calculated. If you put VSH equal to 0 in this equation, that means we have a clean reservoir, then this equation will change to our classical RC equation to calculate the formation water saturation in our clean reservoir. So applicability of this model, as I mentioned earlier, this model generally works better when we have saline formation water. Generally this model has been observed to give very optimistic result when the porosity is less than 20%. Another model is our fertile and hammock, where the water saturation can be written as under root of F or W divided by RT, that is for a value of n is equal to 2 minus VSH into RW divided by 0.45 E into RSH. So you can see this is our classical RC equation water saturation, and this is our can be called as our cell correction. So this is the excess conductivity or additional water saturation which you have calculated if cell is present, if not accounted for. So this term account for the excess conductivity of our cell formation. Once again, if you put VSH equal to 0, you will have clean formation equation or only this term. Another one is Indonesian equation, which can be given as according to this equations. So you can see again the input is needed in terms of cell content, cell volume is needed, and RW formation water ratio is also needed. So this equation can be used and to calculate the formation water saturation. And you can see, if you notice that the porosity is effective porosity, this is not a total porosity model. We need the effective porosity of the reservoir to be used in this equation. Once again, Indonesian equation is generally observed to work best in low salinity environment where salinity is up to 20,000 ppm for NaCl. Now, non-VSH based model, that means the models which can be used to calculate water saturation which does not require the input of salinity of the formation. That means their cell content is not needed. Instead, the excess conductivity is defined by our cation exchange capacity. So earlier model, they were including two terms which were the VSH based model or cell volume based model. They were including one term, that is the cell content, and second term is the RSH. So by including the both the terms VSH and RSH, they were calculating the total excess conductivity offered by our clay. But non-VSH based model, they are going to utilize the value of CEC or QV to account for the excess conductivity of our clay. So there the parallel conductance of our clay and the pore fluid inside sand grain model can be used to prepare a non-VSH based model. For example, in Waxman and Smith's model, we can define ROH F star into RW divided by 1 plus RWB into QV, and RTH F star into RW divided by SW raised to the power N star plus RW into B into QV into SW, where F star is defined as 5 raised to the power minus M star. So here N star and M star are called the Waxman-Smith cementation exponent and the saturation exponent respectively. So these exponent M star and N star, they apply to the total pore volume and they are not limited to the only our effective pore volume or where the mobile pore fluid is present. That means if you are modeling the, let's say, ratio of the formation, then the tortuosity of the total current path or the both the current path is taken into account while defining our M star and N star. So these value can be determined in the laboratory, and you can see in the input we do not have any VSH and RSH. Instead we have our cation exchange capacity when defined in terms of pore volume. The cation exchange capacity must be known to calculate the water saturation using any of our double layer model or non-VSH based model. So laboratory data is needed to calculate the cation exchange capacity. It cannot be calculated from the well log. So if you have taken core sample, and you can analyze the core sample for its cation exchange capacity, and that value can be used in Waxman and Smith's model to calculate the formation water saturation. Once again, I have not given you the derivation of this equation. You can also use another model which is called the dual water model, where you can see in this equation of the dual water model, both the water inside our pores, inside our reservoir rock, and water inside our clay or the bond water are separately calculated, and they are properly defined in our dual water model, and then the dual water equation can be used to calculate the formation water saturation. So I am not going to discuss the derivation of Waxman-Smith model or the dual water model, as the time is limited in this course, everything could not be covered. So those students, those who are interested to go into detail about our VSH model, about the derivation of the Waxman and Smith model and the dual water model, they can refer to different books and you can easily find the derivation of such models. Once again, since M star and N stars, they are defined for the total pore volume. That means here the porosity and saturation must be our total. That means total water saturation and the porosity must be total porosity in this equation when we are applying this equation to calculate the water saturation. So if we have total water saturation, you can also calculate the effective water saturation. So if we have the data about the cell volume, cell porosity, then you can use the total water saturation to also calculate our effective water saturation, as we have discussed during the density law lectures. Now, let us take an example of water saturation calculation in Selly sand. Now, if you see in this law, this green shading curve in the gamma ray law, they define our pure shell section because the gamma ray value is maximum. Now you can see here on the last column, we have a number of models which have been used to calculate the water saturation. In the second track, you can see we have the residual log. So by reading the value of RFH in the pure saline zone, we can calculate an average value of RFH to be used in our different water saturation equation. Here you can see residue is high, that means this might be a potential porous and permeable formation. And you can see the gamma ray log value is low at many places. Here it is little bit high. So overall, it can be defined as having a zone with low gamma ray values, and this particular section might have some cell inside it. It may be a Selly sand zone because residue value are still high. That means it might have still hydrocarbon, but the gamma ray log value is high. That means it may have some cell inside it. So if you look at the gamma ray log, you can define this green shading zone as clean zone and this pink shading zone as a Selly zone. So this is a clean sand and this is a saline sand. Now look at the porosity values. You can see in Selly sand zones in the pink shading, the total porosity and effective porosity have been calculated. You can see both the values, they are not same, they are differ from each other. In clean sand, the total porosity and effective porosity is almost same. So you can see the total porosity is higher in Selly sand. That means it might have some shell content. That's why total porosity is more than effective porosity, because the total porosity will also include pore spaces occupied by our bound water. Now coming to the water saturation calculation, in the clean zone you can see all the water saturation equation, they are giving you the same water saturation values. Whether the dots which are co-derived water saturation, they are also matching with the almost all the water models. So black one is our Archie, the pink one is our Semendu, green one is our Indonesian, and this dotted line, orange line is our fertile equation. So you can see in the clean zones, all the models are giving us the almost same water saturation because the formation is clean, and all the models, whether Semendu or Indonesian or fertile, they will be transformed to the Archie equation if the value of VSH is equal to 0. Now in Selly sand zone, you can see the Archie equation, it is giving us water saturation close to 1, this black curve. But other water saturation model, which are the Semendu, Indonesian and fertile, they are not giving water saturation close to 1. In fact, the Semendu is telling us the water saturation is close to somewhere between 0.3 to 0.4. Same is case with the Indonesian equation. The fertile equation is also overestimating water saturation, at least in some places. So overall, it could be seen here that our Archie equation is overestimating the water saturation. So this is a Selly page zone, this have hydrocarbon, but if you have used the Archie equation, you must have missed this zone. So Archie equation could not be applied in Selly sand equation, as we can see from this analysis. So we should be using any of the water saturation model, whether the Semendu, fertile or Indonesian, or any model which include the CEC or the cation exchange capacity in the formation water saturation calculation. So you can see even in this interpretation of well logs, water saturation value are different by different models. So which one is right? Whether it is Semendu model or whether it is our fertile model or Indonesian model, water saturation is right. How to determine the best fit or how to choose the best fit in terms of water saturation model for your reservoir? Because every model may have been designed with certain assumption. So not all models will provide a good water saturation estimate for your reservoir. So One practical approach to determine the best fit water saturation model for your saline sand reservoir is to use the cross plot between formation water saturation and VSH. That means formation water saturation calculated by the any of the saline sand model and its plot cross plot with the cell content. So this way I can compare different saline sand model by using this cross plot and pick a right saline sand water saturation model for my reservoir. So what we have to do is that we have to draw the cross plot between the cell content and water saturation. Let's say I'm using any particular model. Let's say I'm using the Indonesian model. So I will calculate the water saturation from the Indonesian model and plot the data, water saturation data along with the cell volume on in a graph paper. So cell content will be plotted on y-axis and water saturation can be plotted on x-axis. I will put the scale from 0 to 2 so that if the model is not working properly, it may give us value more than 1 or it may give us value less than 1. And where do I have to do this cross plot? In a water bearing formation. That means below the free water level. So if my model is a very good fit for my reservoir, that means my model can accurately predict the water saturation in my saline sand reservoir. Then for low cell volume, SW should average 1 confirming the water salinity and cementation exponent M. That means I have used the right value of M and right value of formation water registry if I am getting formation water saturation equal to 1 in low cell content reservoir. For example, let's say I want to calculate the formation water saturation in a clean reservoir where I have low cell content. So then all the cell sand equation should give me water saturation equal to 1 in a water reservoir which have very low cell content or if it can consider to be clean, because at this is close to 0 all model will convert back to our RC equation. So the value of formation water registry and cementation exponent M could be checked if only I am getting water saturation close to 1 in low cell content section. Now in other section where I have high cell content, then the model accuracy will depend upon whether my SW is continue to average 1 as VSH is increasing. So in water zone, even if VSH let's say 50% or 60% or 30%, whatever the values, at high cell content value of cell content, my cell sand models should give me water saturation of 1 in a water zone or in a water lake. So as you can see in this cross plot, my values are almost equal to 1 even if VSH is increasing for the saline sand model for which this cross plot has been plotted. That means that saline sand equation is a good fit for my this reservoir to calculate the water saturation. So this way I can choose the best fit water saturation model for my saline sand reservoir. For example, if you see in this figure, if my saline sand equation is not a good fit for my saline sand reservoir, so you can see I can have a model which could be under correcting. That means we know that Archer's equation is going to overestimate the water saturation in a saline sand reservoir because Archer's equation does not account for excess clay conductivity. So I am using saline sand equation and it is also overestimating my water saturation in water lake. In water lake I should have water saturation of 1. That means it is not able to correct the water saturation for the presence of cell. Now second could be the overcorrection. That means water saturation in water reservoir for a particular saline sand equation is less than 1. So that means saline sand equation is giving me water saturation less than 1 in a water reservoir, which is not possible. That means we are over decreasing the water saturation for compensating the clay effect, which is again not desirable. I should have water saturation in water lake equal to 1. So this way you can plot the water saturation data by different saline sand equation in a water reservoir, in a water lake, and see what is the water saturation that you are getting. If you are getting water saturation close to 1, that means it is a good equation for your practical application. So practically how you can decide which model is a good fit for your reservoir. You can always look into the literature about a particular model, in what condition this model will work best, for what type of clay it could work best, what is the salinity range in which this model can be applied. So before using any of the water saturation model, first check about the what is the model based on, what is the hypothesis of this model, and in what condition it could work. Then only use a particular model to calculate the water saturation in your saline sand reservoir. So this is about saline sand analysis. I have not gone into too much detail in the saline sand analysis. I have only given you a very brief introduction of different concepts in our saline sand analysis. Particularly, I have not focused much into the detail of how to distinguish between different type of clay and how to determine the clay distribution in our reservoir. So dispersed clay, laminate cell and structural cell distribution, how it could be determined in our reservoir had not been discussed. So because of the time constraint in this online course, everything cannot be discussed. Some of the concept could be later explained in our practical classes. So this was the last theory classes on our course on petroleum formation evaluation. So over the past 10 weeks, we have discussed the many of the fundamental concepts and techniques of formation evaluation through well logging. You must have gained a comprehensive understanding of the different concepts, methods, techniques which are employed in well logging for formation evaluation. We have gone through different types of well logging methods, different types of well logging tools. We have discussed how different wireline logging tool works, what is the tool measurement, or what is the data recorded by the tool, and how the tool data or the well log record is converted in terms of useful information such as desired formation rock and fluid properties. So we have covered a number of well logs. So we have tried to include all the conventional well logs which are run in routine well logging operation. For example, we have started with the mud log. We have discussed how mud log and cutting analysis and the core analysis can give us very useful information about our formation. Then we started with the SP and the gamma ray log, which could be used for our identifying the different potential hydrocarbon zones and marking the bed boundaries. We discussed the residuity logs to find out the where the hydrocarbon zones are located and also calculate the formation water saturation. Then we also discussed the our porosity logs which are used for the porosity computation from the log data. So density log, neutron log and sonic logs were discussed. Thereafter, we discussed the different well log interpretation techniques. For example, we used different types of overlays, cross plot, and how they can be used to identify hydrocarbon zones, calculate water saturation, calculate effective porosity or total porosity, and identify the lithology of the formation. So mineral volume composition of sand, shale, carbonate can be estimated from the our well log interpretation techniques. Now, in the last week of the course, Dr. Santan Ghosh will take you through a practical session where we are going to use real well log data from an oil and gas field to interpret the different formation rock and fluid properties. So whatever the concept that we have discussed, so density log, neutron log and sonic log will be taken along with the ratio log data, and the gamma ray log data will be used to interpret the formation rock and fluid properties about our reservoir formation. So how to calculate density porosity, how to calculate sonic porosity, or how to use the cross plot to calculate the porosity of the formation, how to identify where scaly sections are present and how to calculate the shell content, how to determine the lithology, how to calculate water saturation. So different concepts that we have already discussed in our lecture such as Pickett cross plot or density neutron overlay. Those concepts will be applied on the real well log data to demonstrate how the theoretical concept that we have studied can be applied on real well log to actually interpret the our rock and fluid properties such as porosity and saturation and calculate the amount of oil and gas in place. So during the practical session, you will see what are the different problems which could be associated with the our well log interpretation. So what are the problem expected when you are actually doing the well log interpretation on a real well log data? So how the textbook interpretation is different or simplified when it is compared to our actual well log interpretation with our real well log data. So now onward from the next 2 weeks, Dr. Sentham Ghosh will take you to the practical sessions.